Welcome to Chapter 9, the sixth screencast for gases. In the previous screencast, we considered the factors that affect speed of molecules of a gas and talked about that a little bit. Now we're ready to look at the relationship between these factors mathematically. And these factors are related by the equation shown above. And in this equation, U stands for speed or velocity. We sometimes use U instead of V as the symbol for speed or velocity. So this is the average speed of the molecules. And it's a particular kind of average speed that you may or may not have heard about before. It's called the RMS speed. And that is an average where the average is done by taking the root mean square average. So we square the speeds and then average them and square root. So it's just a slightly different way of doing the speed or doing an average than you may normally be used to. In this equation, R, of course, is the gas constant. And as we'll see, we'll do it in somewhat different units than we have before to make agreement between the units of T, which is temperature, which, as you might suspect, must be done in Kelvin, and M is the mass, molar mass, of the gas particles that we are dealing with. And soon we will use this equation in calculations, but next let's talk about the relationship on a molecular level just a little bit more. So if we look a little more deeply at gas behavior via the kinetic molecular theory, and we look at the effect of factor 1, which was, of course, temperature, the effect of temperature on speed of the gas molecules, well, if the temperature is higher, the gas molecules are traveling faster on average. If the temperature is lower, then the molecules are traveling slower on average. And the effect that that has on, for example, pressure, if we have a constant volume of container, then if the gas molecules are traveling faster, they are going to hit the walls of the container more often and with more force. And those factors both, or those changes both increase the pressure of the gas in the container. And of course, if the molecules are traveling slower on average because the temperature is lower, then they'll hit the walls of the container with less force and less frequently, and that's a lower pressure. So we can explain pressure in terms of, or how it changes with respect to temperature in terms of the kinetic molecular theory. We can consider the second factor as well, which was molar mass, and the heavier particles will travel at slower speeds, the lighter particles will travel at higher speeds, presuming, of course, we're dealing with the same temperature for both. And this can be heard, in fact, if somebody breathes in gas that is less massive than air, for example, helium gas, the pitch of their voice changes. It goes up quite a bit because helium molecules at the same temperature as air molecules will travel at a much higher speed, and that makes sounds that are created within that gas have a much higher pitch. And of course, if somebody were to breathe in some heavier gas than air, higher molar mass gas, then the sounds that they make would have a lower pitch because the molecules on average are traveling slower. If we change the volume of a gas, well, here's a container with gas molecules moving around, hitting the walls of the container with certain force, certain frequency, and exerting a certain pressure. And if we don't change the temperature but do decrease the volume, then the gas molecules, even though they're not traveling at any different speed and they don't have any different kinetic energy, will hit the walls of the container more frequently, and that will increase the pressure due to the more frequent collisions. And of course, if we made the container larger, then the reverse would be the case. We'd have less frequent collisions and a lower pressure. And we can also use the kinetic molecular theory to explain Dalton's law. If we have more than one gas in a container, all of the gas molecules are going to be exerting pressure due to the force and frequency of their collisions. All of the gas molecules will occupy the entire container, and so the volume will be the same for all gases, and they're all at the same temperature. And so basically the pressure is just simply due to the pressure of one gas molecules hitting the sides of the container, walls of the container, and the other gas molecules hitting the walls of the container, all added up. One of the things we didn't do in the previous screencast was actually calculate a molecular speed for some molecule. So let's do that. And let's pick, say, oxygen gas at room temperature as a representative example calculation. Well, to calculate a molecular speed, we use the relationship average molecular speed, URMS, equals square root of 3RT over M. We're going to do this for oxygen gas at 25 degrees Celsius. And when we plug in our numbers, there's a few things to pay attention to. 3, of course, is 3. What we're going to use for our gas constant is the R in the units of joules per Kelvin mole. And in this set of units, it's not 0.08206, but it's 8.314. And then 25 degrees Celsius, of course, is 298 Kelvin. And then the molar mass of oxygen is 32 grams per mole, but we're going to convert this to kilograms per mole, so 32 times 10 to the negative third kilograms per mole, for the following reason. Now you can see that the Kelvin and the moles will end up canceling, but the joules doesn't look like it's going to in any sensible way unless we realize that a joule, so we'll go back to that, a joule is really a kilogram meter squared per second squared. We haven't dealt with this particularly. This is kind of a physics sort of topic, but a joule is a kilogram meter squared per second squared. And so what that means now is when we start canceling, the Kelvin will cancel as we noted, so will the moles. But now kilograms also cancel, and then we're left with meters squared per second squared, but that's going to be square rooted. So we'll end up with meters per second, which is a perfectly reasonable thing for speed of a molecule. So plugging in everything, take the square root, we get 482 meters per second for the average, the root mean square speed for oxygen at 25 degrees Celsius. And you might want to make sure that you get the same number as well. 2 other quick calculations just to sort of get a sense for how speed changes with temperature and molar mass changes. So let's now try a calculation for oxygen at a higher temperature, 125 degrees Celsius. Plug everything in, exact same setup as before, except 398 Kelvin rather than 298. We, of course, expect the root mean square speed, the average speed, to be higher than it was before, and it is 557 meters per second. Note that's not a lot higher than the 482 meters per second we had before, but it is definitely higher. And let's also try a calculation for hydrogen gas. Now at 25 degrees Celsius, since hydrogen's much less massive than oxygen, we'd expect this to have a much higher, or at least somewhat higher, average speed for its molecules. And you might see if you can predict how much higher you think it might be. So we plug in our values, and as again, same as before, except now the molar mass is 2 grams per mole or so, and that works out to be almost 2,000 meters per second, 1,920 meters per second, which is way faster than oxygen even at the high temperature. So you can see the big effect of smaller molar mass. Here is just a table showing some average molecular speeds for different substances: hydrogen, helium, water, nitrogen, oxygen, and carbon dioxide. These are at room temperature. So you can see, of course, as the molar mass goes up, the average speed goes down, and you get kind of a sense for sort of scale of these things. They're hundreds to thousands of meters per second. Pretty darn fast. Now you might be wondering how molecular speeds are actually measured. And we can, of course, put a radar gun on cars and determine their speed directly. And we can use a radar gun on a softball or baseball being pitched and and measure its speed. But we can't really put a radar gun on a molecule. That is not particularly doable, but there's sort of a clever way that we can determine molecular speeds using the apparatus that's shown here. So we have an evacuated container. We have a little motor that'll drive an axle that has a couple of discs on it. And then we have an oven that's hot, of course, and it's going to be a source of gas molecules. So gas molecules in the oven are going to escape through a small hole here. They'll come out as a beam, and then there's a little disc with a hole in it that kind of makes sure that the beam is very narrow and focused. And as this beam passes in this direction, we have these discs that are spinning, and the first one is a chopper disc. It has a little gap there, and so when the beam of gas molecules is lined up with this little slit in the disc, then the gas molecules will pass through and hit the next disc, which is a detector. But all the rest of the time, when this disc has the slit not aligned with the beam of gas particles, then no gas particles will get through. And now, of course, since this the two discs are both rotating along as this axle spins, then what's going to end up happening is the beam of gas molecules will not hit directly across from where this slit is. They're going to be a little farther along over here, because by the time the particles travel from here to there, this second disk will have rotated somewhat. And if all the molecules traveled at the same speed, then of course what would happen is they'd all hit in the same place on this disk, the second disk, the detector. But this is what we find actually happens. And so we can essentially just sort of count up the number of molecular strikes or hits on the detector, and we can see that we have some fast molecules that hit the detector before it's rotated very far. We have some slow molecules that hit the detector after it's rotated almost all the way around. And then we have more molecules hitting in between, and you can see that we could essentially make a graph out of number of particles at particular speeds, and that's how we get the Boltzmann distribution, at least experimentally. Okay, now here's a couple potentially fun factoids. I don't know if you have any kind of idea of the number of collisions gas molecules make with each other, but clearly it's going to be a very large number of collisions. But could you predict that it would be as high as, let's say, 6-something billion collisions per second for oxygen at 25 degrees Celsius, and for hydrogen, a lighter gas, way more than that even, 14 billion collisions per second? Kind of hard to wrap your head around just how frequently these molecules collide with each other. So even though they're far apart on an atomic scale, a molecular scale, they really are traveling very fast, and they don't have very far to travel. A couple other fun factoids. Average distance between collisions. You might guess that it's going to be not very large, because atoms and molecules are so small. And for oxygen at 25 degrees Celsius, they travel about 7.2 times 10 to the minus 8th meters between collisions on average. And for hydrogen, about 1 times 10 to the minus 7th meters. So, a 10 billionth of a meter or so kind of values. So pretty darn small distance between collisions, even though that's a big distance in terms of how far atoms are apart from each other.